Hello everyone, welcome to the next lab. So previously we have taken 3 different steel samples of varying compositions and strain hardening amounts. So we have our 1018 cold drawn sample, we have our 1018 normalized sample, which ideally should be softer and more ductile than our 1018 cold drawn. And then we have our 1045 cold drawn, which ideally should be the hardest and the least ductile out of all 3 of our samples because it is both strain hardened and it has extra carbon thanks to the 0.45% carbon in its composition. So in lab 2, the main purpose of the lab is we want to prepare metallographic specimens, and what that means is we want to look at our metal samples that we broke, things like our dog bone here, and we want to see what happens on a microstructural level, microscopy scale level to the metal, what makes them different. A lot of material science properties, while they can be easily tested in, say, our tension machines or our hardness testers like we did, they can also be predicted relatively accurately for several properties if you're able to observe what we call the microstructure, which is the microscopic structure of a material. The way we do that is we need our sample to be extremely well polished because we're going to be looking at high magnification, so any sort of small bumps or scratches will basically appear to be a canyon on the surface and make it really difficult to image. And we're also going to etch our samples to reveal these objects called grains, which you may have covered in the class. If not, you're learning about them now. And the size and shape of these grains, which are things that build up macro scale objects, or these little tiny regions of uniform crystal structure, the size and shape of them define how the material will react when put under stresses and loads and in different environments. So, to make this metallographic sample, we're going to take our bars, we're going to what we call section them, which means we're going to cut them with an abrasive saw, then we're going to mount them in a polymer puck, a little plastic puck, so we can hold it, and then we're going to go through increasingly finer polishing steps until eventually we turn this thing into a mirror finished surface, and then we're going to chemically etch it. So first step is we need to make samples of this. So for these, each of our tensile bars, we're going to cut 2 samples from it, both of which are going to come from the grip side. So the first, we're just going to cut about a ½ centimeter long grip section. So we'll have, and we'll mount it so it is faced this way. So we'll have a circular cross section. And then the second one, we're going to cut it this way, long ways, and we're going to look at the flat face. So we'll have a rectangular cross section. So one, we will be kind of looking at this surface, and the other we will be looking at this surface. So kind of going down parallel to the drawn direction. And ideally, we should see a different microstructure, especially for our drawn bars, as they have been pulled during formation. So their grains will be oriented preferentially in the axis of pulling. So to start, we have our abrasive saw here. I'm going to show it to you. So this is just an abrasive saw. Our big wheel is this polymer wheel here. It's plastic. Embedded in it are little diamond chips. So it's not sharp, but it's very abrasive. And if you spin it really fast, the diamond chips can cut pretty much any metal and some ceramics, depending. We have our grips down here where we hold our sample, and this saw just slides forward and cuts through our sample. It is water cooled, otherwise this saw can heat up and explode, so we use water cooling to keep that, and also by water cooling it we make sure not to change the microstructure, because if we add heat to this bar, it's likely we will change what it was when we tested it. So heat affects the microstructure. So I'm going to mount this guy in the stand, in the saw, and I will cut samples from each of our 1018 and our 1045 samples. So I'm gonna go ahead and do that. So this is all self-contained inside this box. But because we're in the lab, we're going to put on our safety glasses anyway. And we're going to cut this thing. So the key when cutting is to use continuous but relatively slow force. Easy as that. The important thing to remember when taking samples out is even though it is water cooled, the blade and your sample, it is metal, which means it conducts heat really well, which means it is likely still quite warm. So if you remove samples from abrasive saw, use some sort of tongs to grab them. And when you're done, you'll have a little sample that looks something like this. So I'm going to cut another one of these from ours, and then I'm going to cut it in half. So we have a rectangular cross section, and we're looking at this surface. So after cutting one of our samples, we now have our 1018 normalized. We now have two samples, one of which is this little circular guy, and one of which is this little square guy, which is just half of this circular guy. So ideally we have two looks at our sample, one of which is looking down the length of our dog bone, the other which is looking along the length of our dog bone. So we kind of get two 90-degree orientations in terms of the microstructure. So that's one done. Repeat this process with our two other samples, and I'm going to go do that off camera, and then we're going to head to the mounting portion of the lab. All right, so welcome to the polishing lab. This lab has basically 4 stations that we will use to complete the rest of the lab before we move on to the microscopes in the room behind me to take pictures. So first step is we need to turn our section samples into pucks that we can hold and polish. To do that, we're going to use this guy. This you see is called PhenoCure. This is known as a phenolic resin, also known as a thermosetting polymer. Thermosetting polymer, what that means is, unlike many plastics and polymers you're probably familiar with, when you heat them up, they become floppy and easier to bend. This is known as a thermoplastic. A thermosetting polymer actually has the opposite effect. When you heat it, it actually hardens and becomes more brittle. So it makes a great material for low temperatures, low pressure. This occurs at around 150 Celsius, and we can make these pucks, which look something like this, with our samples sitting in them. So to make them, we're going to use these heated presses here. I'll show you how they work. So here at the top, this is our 2 parts that we sectioned. You see, we just put them on this little steel plate here. On the bottom are all our controls. So we add in the polymer, and we're going to compress it with a force. Here we're going to use 15 kilonewtons. Then there is a heating time where we heat the polymer to cause it to harden and solidify. That's for 7 minutes. And then there's a cooling time where we cool it off so we can hold it more easily with our hand. That's for 3 minutes. There is a temperature setting. Here we're going to use 150 to set it. And then there's an up and down arrow to raise and lower the stage, and a start and stop. So to start, we put our samples on the top there, and then we are going to hit the down arrow to lower the stage. See, our samples are going down. And now we need to add the thermosetting polymer. This stuff is rather messy, which you will see if you ever come in this lab. There's this polymer everywhere. It's basically like sand, so it's very easy to spill. Luckily we have these handy dandy funnels, so we're just going to put a funnel into our nozzle. And to make a what I feel is a pretty appropriately sized puck, use 1.5 scoops of this polymer. It looks like this. So that's 1, and then 1/2. And then to seal the chamber, we have this little cap here. It has threads on the inside. The cap has threads on it, and you simply press the cap on there and you twist it until it is just hand tight, and then you loosen it about 1/8 of a turn. That helps remove it near the end. And then you go ahead and hit start, which is down here. So our press is coming up to press it against our cap lid here with 15 newtons of force, and then, or sorry, kilonewtons of force, and then it's going to heat it, then it's going to cool it, and because we have 7 and 3 minutes of heating and cooling, this will take 10 minutes, and when we're done, our sample will be done. And each group will make one of these. This is the key point to remember at this point. Once you have sectioned your part, do not mix them up because all of the parts look the same. So whenever you pick, a key part of making metallographic samples is after you cut them off from their larger piece, you label them somehow or keep very close watch of them so you don't mix them up, because at that point there's not much you can do about it. So I'm going to do these other two, and I will see you in 10 minutes when this is done. Hey, so 10 minutes have passed, our samples are done. So to take them out, it's really easy. You just unscrew the top, they pop up, and you press the up arrow on the press. When you're done, sample comes out in a puck like this. And here are our two cross sections. And it's very important right now that I label these. This is the 1018 normalized samples. We have this little scribing pen. Basically, you turn it on, and this is a little guy that just goes up and down, kind of like a tattoo needle. And this polymer is pretty soft, so you can just kind of write on the back of it. So here we go, 1018 HR, more or less. And now that we have this, we can go to the next step, along with our other two samples, which is rough grinding, I guess it is called in the handout. So let's go over to the other side of the lab. So here are our 3 polishing stations. There you go. Each of these is the same machine. We just put a different sandpaper wheel on top of it. So initially, when we section our sample, the abrasive blade from the cutoff saw does a lot of local damage to our sample. It heats it up, it kind of gums up the metal a little bit, it scratches it really severely. So in order to get to our mirror finished final surface, we need to remove the damage from our abrasive saw, and then each machine, each of the 3, is a less rough sandpaper pad. So basically we use the roughest initial sandpaper to remove the damage from the saw. We use the next roughest to remove the damage from the first one, and then we use the third one to remove the damage from the second machine. Each of which consecutively makes our surface smoother, and it removes damages and scratches until eventually we can move to the polishing stage, which is the last 3 machines that we'll use. So each of these, it's fairly easy to operate. There's an on-off switch, there is an RPM setting, and there is a water setting. So these use water to basically by using water, they kind of carry off the debris as you polish the sample, so the sandpaper lasts longer. The sandpaper is just sandpaper like this, and on the back is written the number we care about, which is the grit number. So you may have done some woodworking in your time, gone to Home Depot, gone to Lowe's, bought some sandpaper, and the roughness is defined by a value known as grit. And the thing to know about grit is the lower the number, the rougher the paper is going to be. So we start with a grit number of 240, and then move on to 400, and then move on to 600 grit. Each of these numbers corresponds to a rough size of particle embedded in the sandpaper to polish. So the key is we go from a low number to a high number in grit. To polish, it's not that hard. It does take some getting used to the technique. Basically, you want to make sure that you are pressing down firmly and evenly, like so. And then about every 15 seconds, you rotate the sample 90 degrees. That is just to ensure that you get an even plane when you polish. After just a few seconds, we went from that kind of gross surface that I showed you initially to this guy, so we can very clearly see our circle and our rectangular cross section. So we're making progress, but this is going to take a while. So I'm basically going to skip to the end of this final machine here. But in general, you spend about 2 to 3 minutes on each machine. Initially, because the damage from the abrasive saw is so severe, you might spend more on this initial first 240 grit paper, but at the end, your sample will be pretty uniform. All right, I'll be right back. So I've finished the 600 grit polishing step for one of our samples, and just for comparison to see the progression of polishing, this is how our sample looks initially when it comes out of the phenolic resin press, and after 3 passes on the guy, we turn into this. So you see there is quite a bit of transition. We go from rough and grungy to pretty shiny, not mirror finish yet, but that is what the polishing stage, which is the third and final polishing step before we go into etching, we need to complete. But first I need to polish these other 2, and then I will meet you at the polishing stage right behind the camera. All right, so after our rough grinding, I believe is how it's listed in the handout, our final step is polishing. So polishing is basically just continued grinding, except instead of using sandpaper pads, which have silicon carbide particles embedded in them, which are very, very hard and used to remove material, we are now moving to these 3 machines, and they use cloth pads, and instead of having the abrasive particle in the pad itself, we are adding a liquid to the pad, this stuff, this little green or yellow goo, kind of looks like milk, yellow milk, I guess, and inside that liquid are diamond particles, so pure carbon, very, very tiny diamond particles. And for each of these 3 machines, the diamond particles get progressively smaller. So again, this is similar to finer polishing steps. So our first machine, this one, uses 6 micron diameter particles. Second uses 1, and our third uses 0.3 micron or 300 nanometer size polishing particles. So the way these machines work, put the camera down. So we have this head that goes up and down. This guy rotates. This head also rotates. So actually, the beauty of this machine is that it is automated, which means you don't have to do anything. So the way that we run test is we take our solution, we spray about 5, we'll say 6 very, very tiny splashes of our diamond suspension. This guy we bring down, it clicks into place. We then take your 3 samples, we place them face down in the machine. We have 3 groups, we have 3 samples, we have 3 holes. It works out perfectly. On the machine, there's a few settings. You see here, we have settings for the RPM speed, the time, and the force that these little guys, which are going to hold down our sample, press at. And then we have, of course, our green go button. So for each of our 3 runs, we're going to use 150 RPM, both the stage and the head. We're going to use 3 minutes and 20 newtons of force. So to go, we just hit the green go button. It starts to go, and in 3 minutes, this will be done, and then we'll move on to the next machine right here. All right, so we've gone through the first 2 polishing auto polishers, and our cross sections now look like this. If you see, you can actually see the reflection in the camera of the surfaces. So we have a pretty much a near mirror finish on our samples, which is really, really nice. We have 1 polishing step left. That is the 0.3 micron. I wanted to add this final little video because the 0.3 micron is really just like our final, just like our slight push to get it all the way to where we want it to be. So the idea behind this is you need very, very, very little. For the 0.6 and the 1 micron, the 6 and the 1 micron polishing stages, we used 5 to 6 little sprays of our bottle. The 0.3 comes in this little bottle like this. It doesn't really spray, it just has an open top. And in reality, in order to get a good final polish, you need to just kind of pour on the stage, and you need about a little bit more than like a quarter size amount of polishing. So this white stuff here. And then throughout, instead of adding more polishing solution, we actually just add some water, distilled water, and that kind of evens it out and distributes and kind of cleans our surface, kind of extends our polishing. So we need very, very little at the end. This is also the messiest last one because it's a little bit thicker than the other 2, so it likes to throw clumps around if you put too much, which a lot of people do. So anyway, 1 more step, and then we're all polished, and then we will go on to etching. The final step is done. Our 0.3 micron polishing is finished, and here is our sample. As you can see, very shiny, very smooth, mirror finish, just like we wanted. So before we go on to etching, which is the final step before the microscope, I need to stress one thing, which you probably heard about in high school and at UT here and in other labs, and that is the importance of cleaning up after yourself. This is just kind of the general safety recommendation or lab requirement, is that other people use these spaces. And in the future, as an engineer or a material scientist maybe, or some sort of researcher, or just as a coworker, cleaning up after yourself is critical. And this lab is messy. It is the messiest lab out of all the ones we're going to do this semester. So I want to stress, if you come into a polishing lab or any sort of research lab in the future, try your best to leave it as you found it, or if possible, maybe nicer than you found it. So before we go on to etching, I'm going to take each of our 3 polishing pads and our sandpapers that we went through, and I'm going to store them in the proper places, and then we will move on to etching. So the final step before we do our microscopy to actually look at our microstructures, which this whole lab is revolved around, we need to reveal our microstructure. So right now our samples are really nice and polished really well. They're mirror finish flat, but we can't actually see the microstructure, the things that make our sample special, the things like the grains, the grain boundaries, the different phases that we see. So in order to reveal these phases, things like ferrite, which is pure iron, or things like pearlite, which is iron and carbon layered on top of each other, we need to reveal them with etchant. Etchant is some sort of caustic mixture that attacks the surface of the material. And for things like metals, they really specifically attack the grain boundaries. So grains are regions where you have uniform crystallinity. So your unit cells are all moving in the same direction, and they're all at the same orientation. But at certain locations, you'll have planes of atoms that will meet other planes of atoms, and they'll be slightly offset at a small angle. This angle is anywhere from 5 to 15 degrees. And the reason they do this is to relieve stress, because to maintain a perfect crystalline lattice, a perfect line throughout the entire sample is actually really difficult, because the sample is not truly uniform. So they have these grains, and at grain boundaries, stress is relieved, and these atoms meet. The thing is, also, at grain boundaries, because these atoms are slightly offset, because they have this angle, they are not at the perfect orientation for bonding. That means their bonds are slightly weaker than inside the grain, inside of a perfect crystalline ordered structure. And that means if you attack it with a caustic etchant, caustic solution that eats away at these boundaries, they're going to attack the atoms at the grain boundaries first, because they are the most weakly bonded. So by attacking these atoms that are at these angles, you basically remove the atoms at the tip, and by slowly removing them, you will widen the grain boundary and dig a sort of trench into the material. And what that will show up in the microscope is dark lines identifying our grain boundaries. So for steels, the most common etchant is a etchant known as Nital. Nital, N-A-T-A-L, is a mixture of nitric acid, 2 milliliters of nitric acid, and 98 milliliters of ethanol. Ethanol, you might have used it before. It is the primary thing in alcohol that gets you drunk. And nitric acid is a very, very aggressive acid that really hates metal, and also really hates organics, which means it will burn your skin severely, even a very, very small amount. So if you're ever dealing with nitric, any sort of extreme chemical, any chemical really that is not, water, it's always important to be prepared, to wear gloves to cover your hands in case of spillage. For nitric especially, you want to do things inside of a fume hood, because it takes the vapors away and not into your face. And we have our face shield to protect me from any sort of splashes. And I have sturdy gloves to protect me from nitric getting on my hands. So I've already prepared some Nital. It is in this bottle. It looks like water. You really can't tell the difference until you open the jug. And if you were to smell it, it smells terrible. But hopefully you don't have to, because it's inside the fume hood. To etch, it is relatively easy. You take these long Q-tips, like so. You dip it in the Nital, and then you wipe it on the surface of your sample, like so. And you basically just want to make your sample wet with the etchant. And for steel, it reacts very, very quickly with the Nital. It etches in about 10 seconds. The way to tell the etching is occurring is our polished surface will turn to a kind of cloudy appearance. It will appear like it's not polished anymore, which it's not, because it's etched. So this is what it looks like now. And I will go ahead and etch one for you, and then show you what it looks like after. When you're etching, you want to make sure you're etching inside of the fume hood if you can. So I dip it, and then I just rub it on the surface. And once it starts to turn cloudy, which it has, I will take it to the sink right behind the camera and wash it off. And then I take my used Q-tip, I put it in a waste jar, which is in the back of the fume hood here, and I'm done. My sample is still wet from the sink, so I'll blow it off with compressed air. But first, Before I do that, I'm going to close my Nitol. A little tricky with gloves, but you can do it. And when all is said and done, your etch sample will look like this, which you can see, hopefully. So the this side here is etched, the right side is unetched. And the reason why it looks cloudy is because as we reveal the grain boundaries, the surface is no longer uniform, so it is no longer reflecting light all back at the same orientation, at the same direction. It's scattering light in different directions, so it's not as shiny. Okay, so an important thing to do when you're new to etching is you etch for a short amount of time, and then we take it to the microscope and check. If you can see the grain boundaries, great. If you can't, you can re-etch for a little bit longer. Sometimes you can over-etch, which is kind of difficult to see if you don't know what you're looking at. But if you over-etch, the problem is you have to go back to our automated polishers and do the last like 2 steps again. You have to repeat, you have to remove material. So it's better to under-etch initially than over-etch. But again, for steel, pretty quick, about 10 seconds, and then you wash it off in the sink. I'm gonna go check to make sure I did an okay job, and once I did, I will return and we will go to the microscope room. Okay, so here is the final step. We have our samples. See, this one is half polished, half etched, and we are going to look at the etched side of each. I have labeled, this one's 1018 CD, and then we have our 2 others as well. So this is our microscope screen, is connected to a microscope, which is on the right of the camera. I'm going to go ahead and put our sample on there. It's a little blown out, so we focus. So this is our polished surface. As you can see, we still have there's a big scratch here. These little guys, these porosities, these are just present on the interior of your sample. It's not always 100% uniform. You'll notice these on pretty much every microstructure sample you look at. So this is polished, 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 but if we go to the side, you can actually see a transition. And here is our etched region. So you see it looks kind of grody. And an important thing to do when always using the microscope is you want to add a scale bar. In this case, our scale bar is this one right here. You click, it adds it to the bottom, but you need to make sure it's accurate. So in order to make sure it matches the magnification which we are using, which is 5, you go to calibration, objective, and then you double click on the one that you want. So right now it's 5. So that means our scale bar is accurate. But this kind of looks like brown mush. We can't really see anything. So let's zoom in. Okay, looks a little better. Let's keep zooming in. That was 10, this is 20 times. Let's refocus. See, we're starting to see stuff. Let's go to 50 times. Let's increase the brightness a little bit. So at 50 times is where we start to see real effects of the microstructure. So this layered, let's actually go one more time. 100 times, maximum magnification. If it goes any brighter. I don't think it does. So let's go back to 50. That's a little dark. So at 50 times, you can start to see our microstructure. So 1018 steel has 0.18% carbon, And a big feature of carbon steels is pearlite. And a pearlite is a layered structure composed of pure iron ferrite and iron and carbon, a structure known as cementite. And it forms layers, which you can actually see if we zoom in. Very, very nice. You see we have these kind of layered structures. So the dark regions are cementite, this carbon base, and the light regions are ferrite, the pure iron base. And let's fix our scale bar, because right now we are at 50 times. So if you fix our scale bar, you see we're at 20 microns. So here is our sample. As you can see, it's pretty uniform. See, there's a big porosity, a void right there. Here's another one. You can tell it's a void often because you can focus into it. You can actually focus on like the bottom of the hole. But we see this is a lot of pearlite and some ferrite in the mix here. So this is with 0.18% carbon, we remember. And this is our cold drawn sample. So this is actually our circular cross section. Now if we go to our flat cross section, which should run parallel to the direction of drawing, we'll go back to 5 times. And if we find our other sample, it's not there, let's go the other way. Here it is. So we find our other sample. Let's zoom in. Let's adjust the brightness a little bit. You can hopefully see kind of lightly we have a orientation that is going kind of downward in this direction. So our grains, when this was formed, were drawn through a die, and that die kind of forces our material to go in a certain direction. And this is a little bit easier to see if you follow the path kind of goes down like this, which is the direction of drawing. And again, if we zoom in, this is 20 times, this is 50 times again. If we zoom in, we again see our pearlite, kind of layers here, and our ferrite. We can zip around. That's a pretty good spot. We have all the fun stuff. We have our ferrite kind of down here. We have a big hunk of pearlite. We have, this is a scratch, you can tell because it's kind of in a direction. And then we have some porosity here. All the good stuff. So to take a picture, this is 50 times. So let's again make sure our objective is correct. It is. You really never want to take a picture without a scale bar because people don't know if your image is, if this thing is an inch across, if it's a mile across, or in this case, if it's about 200 microns across. So we'll just go to the snipping tool. This is honestly the easiest way to save photos. And there we go. There's our picture. Scale bars included. And we can go ahead and save that as our 1018 CD. This is 50 times, and this is parallel to the rolling direction. If you wanted sometimes it's easier to see more macro scale in terms of the drawing direction if you zoom out. So in this case, our kind of forced orientation is more easily noticeable up and down like so. But again, our scale bar is wrong. This is 10 times. Okay, so that's 1018 CD. Now let's look at 1018 HR. Okay, so we're going to start with our circular piece, I believe. Yep, all right, so this is our circular cross section. Everything looks pretty small, so let's zoom in. 20 times, 50 times. So this is our hot rolled or normalized. You can actually see our heat treatment actually made our, looks like our average grain's a little smaller. So you can hopefully see, if we go back to objective, 100 times. This is as bright as it gets, unfortunately. Our grains, so a single region of kind of perlite would be a grain, and a region of ferrite would be a grain. So it looks like, you know, this ferrite grain is perhaps 15 microns across and, I don't know, 3 to 5 microns wide. This one, you know, is 20 across and maybe 10 wide. If we move around, you can see so focusing becomes a little bit trickier at these magnifications. That's why a flat surface is really nice. Make sure that you polished your sample so it's flat. So if we zoom in on the zoom in, you can hopefully see some perlite here, some layers. Let's zoom out, let's go to 50 times. So our perlite layers here are much closer together, but our grains are way more defined. And if we go back to our low mag, and then we go to our horizontal section parallel to the drawing direction, you can hopefully see so I'm looking at this, I still believe we have some sort of linearity, but it is less prominent. This is 50 times. So here's our grains. We have nice perlite here. No really big voids. This sample is maybe slightly over etched. When you get these grains that look extremely dark like this, often that's a mark of over etching. So here's some more. So our hot rolling seems to have kind of made our grains more circular in shape, like so. But it also has made them slightly smaller, which is a feature of heat treatment sometimes. It can happen. So when you would measure your average grain size, you would likely find that is the case using our lineal intercept method. Okay, and now let's look at our final sample, which is 1045 CD. 1045 CD, you might remember, has the highest carbon content, and that becomes pretty quickly obvious because this is quite a bit darker, quite a lot less light ferrite regions compared to our 1018 samples. But if we zoom in, just 20 times, let's go to 50. We do see it is pearlite. So we do have pearlite here. We have pearlite down here. We have some pearlite in this region. But you'll notice our ferrite regions are a little bit less significant. And right now we're on 50 times. So let's make sure our scale bar is right. If we go to a different location, about here, this region seems to have a little more ferrite, but we still have our kind of layered pearlite here and here. If we zoom in to 100 times, it's darker, but the pearlite becomes slightly more visible. And let's go look at our square cross section, which is parallel to the drawing direction. That one is down. Nope, it's up. So this kind of goopy mess you see here, this non-uniform mess, this is our polymer puck. So if you see this, you're not looking at your sample, you're looking at the polymer. So keep looking for it. Here we go, and here is our sample. And I feel like the drawing direction is pretty well noticed here on the vertical lines. It is quite a bit darker. Let's zoom in again. It's 10, it's 20 times. There we go, let's do one more. 50 times. So here you can see we have individual ferrite grains. These little guys here are our grain boundaries for ferrite. You see they're about, I don't know, 10, 15 microns. And we have lots of pearlite, lots of this layered structure, kind of this whole central column. It appears is some form of pearlite. And let's move around a little bit. How about here? So this guy in the top right, this is a void. You see we can kind of focus on the void. We can focus on the depth going into it. So that is a hole, that is not a phase. But again, we have ferrite, this vertical line with some grain boundaries. And we have our pearlite, our layered structure. And let's make sure our objective is correct, is 50. I don't like that hole, so I'm going to move somewhere else to take a picture. This looks pretty nice. There we go. And to take a picture, we'll just use our snipping tool again. And when you're saving your picture, it helps me, might help you as well. When you name it, to do the sample name, which of the two cross sections you're looking at, the circular or the square, and also the magnification. So in this case, it is 50 times magnification. Okay, so that is our 3 samples, and for the lab, you need to take, I believe, 2 pictures of each. So you could do one at low magnification, maybe 20 times or 10 times, and one at high magnification, say 50 or 100 times. And you really want to be able to see the pearlite and the ferrite. And you'll need that in order to measure average grain sizes. So that is the lab. It's a lot of work to take these microscopy pictures, but it needs to be done pretty much every time to get these high magnification images. If you want to take these samples and look at them in even higher magnification microscopes like the scanning electron microscope, the SEM, you have to polish it, you have to etch it. We have to go through this. It is a rite of passage, we'll say, and ideally, we won't need to do a lot more of it. Maybe for lab 3, we might, a little bit, but it will be much faster once you've done it already the first time. So that is the lab. I will see you all next week.